The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So I'm Connolly is with McHugh Construction, and he will be talking about the NOVA support for a tower crane in one of his projects.
Thank you, and thanks for the opportunity to speak. And it's also a privilege to speak after all these other previous speakers. Really, some great topics. So mine, though, is pretty specific to one particular project. It doesn't have the grand vision or multiple experiences. This is just one particular project that we had experience with in Chicago. So some of the learning objectives here is just basically talk about some logistics, the considerations of putting a tower crane for a project in particular in a tight urban setting, some of the issues related to tower crane assembly and disassembly, and the requirements for a mobile crane installation in the public way, in particular for in the Chicago or any urban area. So this is a marketing video that the developer put together, kind of shows the area. So it's a small little infill project. It's a 17-story addition to an existing parking structure. So the building there is the kind of the glowing one. It's just immediately to the north of Trump Tower and adjacent west to an existing 55-story building. The site itself was originally a project that McHugh built in the late 70s, in 1979 approximately. And it's the neighboring structure, which the site's on, is a 55-story building with a 4-story parking garage. They had some anticipation to do some vertical expansion at some point. Anyways, the time passed, and the building originally was an apartment building, and then it went to a condo, and then the parking garage became a separate condo association. And somebody was wise to that there was some foundations that had possibilities, and a developer bought the air rights from the parking garage condo association and basically planned this. So it's a pretty neat infill project in downtown Chicago. So and it's adjacent to a 1930s Wabash Viaduct. So from a construction perspective, there's a lot of challenges. The design team that helped us pull this off, Belgravia was the developer, BKL was the architect, Eamonn and Case were the structural engineer of record. They're out of Atlanta. In particular to this topic, the people that we were relying on, we collaborated very closely with the engineer of record, Eamonn and Case, flood testing, and Terracon, both out of Chicago, and then bottom left, Morrow Cranes. They were very, very helpful in basically helping us get the right piece of equipment that's going to work for this project. So just speaking about logistics, every job, logistics is the key, and for high-rise work, it's critical. And so for a project like this with the really tight site constraints, figuring out how you're going to actually make deliveries, have materials show up, it was critical. Since we were immediately adjacent to this 55-story building, we had their public drop-off area, we had to protect the public. So one of the primary things was we basically decked over the entire drop-off area, which is what you see in magenta on the top and to the right. And then that whole decked-off area then became like double duty. We used it as a lay-down area and an area to build rebar cages. So that was like protection as well as like a staging area. We had the skip hoist, which is like squished in at the south end of the site, immediately adjacent to the Trump Tower, and then the tower crane. This here is showing the actual final selected spot for the tower crane. The building is relying on existing belt caissons. There are no new foundations. So typically with a tower crane installation, there's typically new dedicated deep foundations, or you're adding on to existing deep foundations. But this here, because we're building vertically expanding up, we had to basically support the crane without any foundation. So we decided to basically cantilever it off the side there. So it was kind of an interesting solution to a challenging problem. So this is kind of showing just how tight things were. So this is a view of the skip hoist. So the view on the right is from the drawings where we're laying out where the skip hoist was and the mast and the loading dock. And then the view on the left is an actual photograph of the actual execution. So you can see how tight this is. So, we're looking down the south elevation of the building. You're looking down the skip hoist mast. You can see the loading dock there and room for one truck to make the delivery. And then there's a public passageway there. You can see a number of people walking along, and immediately the curve there is the ramp for Trump Tower. And so it like really is like just finding the right spot and then squishing in the necessary logistics. Further talking about, again, making space to do the work. This is this canopy over the drop-off areas, as I spoke previously. So there's a lot of effort and engineering, again, to obviously protect the public and properly design a protection system that's going to, be, safe and adequate, but also double duty to be allowed to use for like staging and actually having our personnel build rebar cages and whatnot. And then because this is a structural slab and we have to keep a driveway open, we're putting in, and the live load that this deck had to support, 250 pounds per square foot, is quite high. We're imposing quite large loads on an existing structural slab. So a lot of effort was done to check that. And so we did some analysis ourselves, and we shared that with the engineer record who's in a case, and we both agreed that we were taking proper care. So as I said, to build a high rise, you need a crane, and so we were scrambling for a spot to locate it. So the solution was to design a floating crane that basically levitates out over the public way. It's projecting west outside the property line 18 feet, and it's 8 feet above the actual sidewalk on Upper Wabash. And so this, the image there you see on your right is from the Tekla model that we developed, and shows the actual vertical expansion of the building. So all those 18 stories plus the crane foundation and the sloping columns and the crane. And then the design, again, I'll just quickly go through this, but this is an actual section view from the submittal drawings. And again, like the crane is a novel solution to a challenging problem. So we basically found a spot to slope columns from Lower Wabash up through Upper Wabash, thread the needle between some existing viaduct beams, and then support a 5-foot thick foundation. So again, we were walking the job as we were pricing it and chasing the job, and obviously you can't bid a job without a solution. So very early on in the process of McHugh chasing this job, we were thinking logistics, and we had conceptually come up with this scheme, which we progressively, as we marched towards winning the job and then executing the work, verifying and validating. So again, we had an idea, and then we kept on basically testing that idea and proving it out, and making sure that we could actually build what we were planning. The design further, obviously we're relying on the existing foundations. So this particular project, we were quite fortuitous. There was very detailed records from the 1970s for the belled caissons from the famed geotechnical firm in Chicago, STS. So we had the borings from the 1970s, as well as the caisson logs, and Terracon, which were the geotech for the project. They basically prepared a report and allowed, basically pressure increases for those caissons. The engineer record utilized this information to justify the vertical expansion. We used that information also to justify the loads that we were imparting on the foundations that we were utilizing. Also, again, we're supporting on existing foundations. So Terracon had done an extensive survey and cores, and verified that the caissons were 5,500 psi, and the columns and walls were 5,000, which we could use in design. So, collaborating with Eamonn and Case, they had developed an ETABS model for the analysis and design of the building. They shared that model with us, which we then took and modified and added in the crane foundation. And so, so we could think also of the stage construction. The first thing that was going to happen on this job was this crane foundation was going to be installed. So obviously we need to consider the loads that are on the system at the initial stage, and then obviously when the building is topped out. So we considered the stage sequence, and verified the adequacy of the structure, the existing structure, as well as the design structure to resist all those loads, using just standard ACI provisions as well as AISC provisions for the sloping steel columns. And then this is just some information just showing the layout. So we have our Morrow 200 series crane. It's just the right crane that's going to fit in there, and it's not the ideal crane we would like to use. Typically, McHugh likes to use a 300 series or 400 series crane, because quite often buildings have rather extensive cores and extensive formwork that need to be lifted. This project, which is pretty neat, is there is no core. It's a moment frame. The actual design was lightweight PT slab and some moment frames for the primary east-west direction. So as a consequence, there wasn't really any heavy formwork to lift. So we were able to optimize the crane to a Liebherr 200 series, which has a much more modest pick capacity. The other reason why we needed to do that was we had pretty much maxed out the capacity of the foundation. So literally we had to dial in the crane to match what we could support. So it was kind of an iterative loop of like finding the right equipment to do the job as well as to match what we could, pull off without actually running into problems with the foundations. And then this is the portion from the climb schedule. So the phase 1, we're freestanding. We're standing on like 8 tower sections. Again, we could have stood up more. Like, quite often when we stand a tower crane, we like to basically put up as much as possible during the installation process. And like, we typically have an initial hook height of like between 180, maybe 200 feet pushing it. Again, because obviously the higher you can go, the fewer tie-ins or maybe the elimination of tie-ins. This one here, again, because the foundation was maxed out, we tuned the crane initial freestanding conditions such that it would like the overturning moment would basically be within a range that the foundation could support. So again, an iterative process with the Morrow engineer to find the right piece of equipment and the right initial condition to match up with what we could support. The image on the far right then is the stage 2 where we had a tie-in and then we basically added in the rest of the sections. And so just as another, I don't know how much people have experience with tower cranes, but like one of the things in Chicago is a big deal is obviously like, where do you store the climbing section? Because obviously putting it up there takes time and effort. So from a constructability perspective, like, you'd like to install it and pin it to the top and then don't have to touch it until you have to like, use it again. But obviously that piece of equipment it weighs something, but more importantly has increased sail area. So by storing the climber section at the top of the crane, you're inducing more wind forces and thereby increasing your foundation loads or your mass forces. So for the initial condition where we're freestanding, because we had such a modest height, we could store the climber at the top and still stay within the capacity of the foundation. And so when we stood the crane up initially, we stood up all 8 sections. And then we, built up, and then we got to level 8 or 9, a couple weeks before the tie-in. We had basically our crane crew come out there and install that climber, and then stowed it there, and so we carried on our construction. So that when we were able to do the tie-in, we already had a climber there ready to go, and then we basically, took out some time on our schedule. So basically thinking about like the sequence of the equipment is very, very important, and trying to obviously optimize the time of your iron workers. And then just a little bit more about the crane tie-in. This is if you design tie-ins at all, or you review engineers who design tie-ins, they have to consider the forces applied to the structure. So the struts basically are delivering either axial tension or compression. They deliver that force to like basically a buttress here. That buttress is above the slab. And it's offset, so you're getting both, basically, the shear as well as, a flexural moment associated with it. And, Morrow was very clear that designers need to consider this. So it's part of the required design effort. And then construction. The crane is the critical path, the first thing that has to happen. And so basically, the superintendent who was going to do this job, like he was like, this has to be done, and all the work that I need to do to get this work done, you need to have your permit way ahead of time, you need to have your shop drawings done way ahead of time. And for this particular project, because it was so important that it all fit, there was a lot of effort just basically validating the geometries and stuff like that, making sure that the struts would actually fit between the existing viaduct beams. And then obviously once we poured the crane foundation, we needed to stand it a couple days later. So choosing the right concrete mix. So we're talking about like getting to 5,000 psi in about 2 days. So making sure you have the right high early strength mix. And also because this crane foundation is as cool and neat as it is, it's not part of the final construction. So you got to think about how in the world you're going to demolish this. So basically building in considerations of how to demo. The photo, you can see that we actually poured columns ahead of time and then wrapped them with some visqueen so that like as a bond breaker. And then we, for the reinforcing bars that we're going to actually pass through those, we had installed couplers so it could basically couple on the bars. So in the demo process, when they start like saw cutting and chipping, they could they could basically expose the columns with no problems of damage, and as well as like just unscrew the bars. And then these are some photos from construction, just kind of showing how we threaded a needle. So the photos on the left and top are showing the struts going through the Wabash viaduct. So again, we thought about this concept when we were first looking at the job, and then I've checked it and double checked and made sure it was all going to work, and then here's the actual execution of it. So we're thrilled that we had the opportunity, and it all worked out and lined up nicely to allow us to do this. The photo on the bottom right is just the corbel that the strut is resting upon, and there's quite the bird's nest of reinforcement to transfer the load. And then the photo here is the completed project. So we've got the tower crane foundation cast. The first section is there, ready to go, and we're ready to erect our crane. So to speak about that issue, because now we've got a mobile crane that we need to use to basically build the tower crane. And because this is an elevated 1930 structure, which is in a delicate state, the city is very, very obviously protective of it. So anytime you have a crane that's going to be on a bridge structure in the city of Chicago, you got to become very familiar with the bridge office. So we put together a set of plans and drawings, and very early in the as we're doing our pre-construction, months ahead of time, we had a sit-down meeting with the city officials and basically talked about our concept, and then basically worked through the requirements that they were looking for, and then provided that submittal and got the approval. Again, all this work happened way ahead of time, because obviously, when you need this, you need it right now, and you need to have all that pre-planning done. So a lot of effort working with our partners at the bridge office to make sure we had the proper approvals and review done ahead of time. And then just a view of the shoring. So the outriggers, we're basically putting down about 100,000 pounds of outrigger force, which is way beyond what the viaduct could take. So we supported it with shoring towers and mats that are on the lower Wabash street at grade. Here's a section view showing the whole assembly process. This is showing the Wabash viaduct, the mobile crane there in the red line work, and then the outriggers supported on mats, then supported on shoring towers onto mats below. And then the blue line work is the tower crane on the crane foundation. So a fair bit of engineering effort and to pull that off. And then this is just the logistics plan. So of course we're in a very urban environment with a lot of businesses all around us, and so the whole process of erecting this crane was going to be very disruptive to the local businesses and neighbors and whatnot. So again, it was critical that we get out in front of that and communicate to all the various stakeholders. So making sure that we made every provision possible to make sure that the people in the neighboring 55-story building could get out and access out. So you can see at the top there, you can see the yellow fencing, which is basically keeping the construction zone clear of access to the drop-off area. And then at the south end there, you can see basically keeping access to the parking garage here next to the Dunkin' Donuts. So again, a lot of planning and communication required. And then this is another just view showing just the staging of how we're going to get access in while we're erecting the crane, but also keeping access available to surrounding buildings. And again, this type of planning, but also more importantly, communication is just critical. Just telling people what you're doing way ahead of time so there's no surprises and angry phone calls or screaming matches. And then this is a photo of the shoring that was required for the mobile crane on Wabash. And the photo on the right there is the nice warm day we had in Chicago too. We were erecting the crane. And then this is a series of photos just showing the progress of work. So the photo on the far right was taken about December of last year, not too long after the crane was put up. And then the middle photo was probably taken about, March or so. And then the final photo on the left with the building topped out was taken roughly around just end of June, end of May, apologies, early June. So the building went really quick, and now we're topped out. We got a beautiful building, and now it's time to take it down. So I think the photo here is basically just right before we started down climate. We're getting ready to basically do the work in reverse. So the key thing is we want to try to do as much work with our iron workers ahead of time. So we basically, in the week approaching the actual disassembly process, we down climbed that crane as low as possible so that it was just above the top of the foundation. So the mobile crane that was going to be utilized to disassemble this could be as small as possible, and the reaches and the height that it had to reach at was minimized. And there's a view of the crane already down climbed, ready to go. and it's gone. So now we have a beautiful crane foundation with no crane on it, and we got to get rid of it. And so we just bring out the breakers and just basically sit on it. And the grousing that I got for how well built this was and the high strength concrete that was in there. And but they, again, they used the small machines. Obviously, they're on structural slabs and taking care not to damage the permanent work. But they were able to get through it, and basically you wouldn't even know there was a crane foundation there at all. So it's been completely erased. So ephemeral engineering. So conclusions, just like, constructability wise, like, when you're offered a challenge, you need to think outside the box. You need a lot of info. You need it fast. And it very much requires a team effort. So this crane installation was very much dependent on everyone's, contribution. And like the old adage, plan the work and work the plan. So with that, thank you very much.